Alright, before we start, I will recommend you to watch these videos first. If you're done, let's get into it. We recall that the nabla or del operator here equals to this summation of partial differentiation operation, which a hat k here is basis correspond to xk component as in position vector. For example, if we have nabla to f here, then it will tell us a gradient along all direction in space. And now the question is, what about nabla dot A and nabla cross A when A here is a vector field along real number field in mathematics? Imagine we have this coordinate system which here is x1, then this x2, and then this x3, and then inside of our coordinate system we have a cuboid here which the edge length here is delta x1, delta x2, and delta x3. And next we have vector field of A as this, which has different value and direction each point just like usual field in physics. And then the important thing here, we need vector field characterization, which lead us then to vector calculus that we can getting start by determine the result of nabla.A and nabla cross A, which nabla.A here is divergence and the other one is the curl. But first, we define the flux of vector field, which is the total vector field arrow get out from the surface that envelope the cuboid here is equals to integral along this enveloping surface to the cuboid, let's say sigma as a region of integration, which sigma here has direction as area facing dot to a vector as the integrand. As we know that this region of integration is about closed surface or in general as hypersurface, which in this case envelop the volume or in general as hypervolume. So to another notation, I denote the integral has circle here, which known as contour integral that relate closed hypersurface integration. And now if we let delta xi here is approach to 0, I denote I because it can be extended to higher dimension, which for the first two terms I have this. And notice that the first term x0 here is about the vector field in the position of the n1 surface here. And then for the second term here, there is delta x1 because we shift the detection of vector field from x0 as delta x1 here, and so on for the other side. Then notice that the n1 I define here is about this direction of phase of the surface. Then the minus n1 here is about this part because delta x here is infinitesimal. Then we can linearize our a vector here. There is mistake in minus n plus here because the direction analysis. And then for the first two terms, we will get the result as this. If we sum to the other phase here, which can be generalized to the higher dimension, we will get as this. And notice that for infinitesimally small delta x here, we will get that this part is about nabla dot A. And for delta x here, for infinitesimally small, we will get that this is as infinitesimal volume as dv. So the sum here, we can replace as integral by Riemann sum. And we combine the equality here as this. This result known as Gauss theorem for divergence. If we let nabla.A as f of x here, we will get the Gauss theorem will tell us about this, which the left hand side tell us about field that go through to the surface, and the right hand side here is a characterization for the source of field itself. For more detailed analysis, the left hand side here tell us about property like its spread or sink property of the field from one point. And the right hand side here tell us about the property for the source as a point. So here if we have f is a positive, then the field will be spread, and if f is a negative, then the field create a sink Then if F is equals to 0, the field has no source because the field only passed through, not produced inside the region. And notice that nabla.A before is a scalar field or scalar function relate to source point property, only need the value or just a scalar. Next, with the same field here, we now analyze in spatial 3-dimension. Here, we have the area, a square just like this. And then we want to know how if we integrate, and we want to know about the property of the field along this loop as L vector here. Again, we let delta x is approach to 0, the field in x0 as before in this. So we start looping from this to this. We will get the result of integration in the first part here as this, and so on for the other path. So we get as this. And again, because of infinitesimal shift, we can linearize this A here. So we get the final result as this. And notice that the delta x here create the small region or small partition of area, which I denote as sigma vector, which the direction of the vector relate to phase direction. And the other side here is about nabla cross A, which the dot product inside here, we leave the A for the component that correspond to each direction vector. So then we have the final integration as this, and then the final result for equality as this, known as Stokes theorem for curl in 3-dimensional vector, because we know that the cross product only well defined in 3 dimensions. And again, let nabla cross A is equals to J vector here as a vector field. Then we plug into Stokes theorem, we will get this result. And notice that the rotational property here we can get from the left hand side integration, but for the right hand side we will get that this J is about rotational source as a pole, not as a point. Pole because this is a vector, so we can draw the pole here as a source of rotational property of the vector field. So for summary, I will split up to 3 categories for differential form, the integral form, and the story behind the scene. The first is nabla.A is equals to F as differential form, and then we have this integral form, which is here we have the story behind as point source of F that create the field as sink or split. The next one, nabla cross A equals to J as differential form, and then the integral form as this, which then the story behind the scene is about pole source of rotation, which explain the vector field has rotational characteristic or not. This second part here relate to solenoidal vector field. That's the simple introduction and proof for vector calculus in the beginning. I hope you enjoy this video. If you like this video, don't forget to share and subscribe. If you have any questions, drop the comment below, and see you later.